Hello students, welcome to Unacademy, India's largest learning platform. I am Abhishek. I did my graduation from IIT Roorkee and my MBA from IIM Indore. So in the previous video, we had discussed about the dual nature of electromagnetic waves. In this video, we will learn further about the developments which led to the Niels Bohr's atoms, right? And this video will study about the atomic spectrum. So let's begin this. Hello students, welcome to Unacademy once again. And this is part 3 of the video, which is about the developments leading to the Bohr's model. Now we had seen part 1 and part 2. If you have not seen those videos, please come revise them once and then come on to the part 3. I am Abhishek Datta. You already know about me, so let's begin this. We'll be taking up two topics of discussion in this video. Firstly, we'll discuss about the atomic spectra. Now this is an interesting phenomena, right? And finally, we'll arrive at the Rydberg equation. So let's quickly begin with the first topic, which is the atomic spectra. Now what do we mean by a spectrum? Before we move on to atomic spectra, you must have heard the word spectrum. So let's clear cut define it, what we mean by spectrum. So when a white light is passing through a prism, you must have performed this experiment in the physics lab. It splits into a series of colored bands known as spectrum. Now you must have seen these sort of colors which are shown on the other side of the spectrum, on the other side of the prism, right guys? And this thing over here, it is known as the spectrum. Now did you know that this spectrum, it constitutes of a major, very big part of a spectrum. Now this is known as the continuous spectrum, right guys? So spectrum again can be divided into two parts now. So the first one is continuous spectrum and the second one is the atomic spectra, about which this video is, right? So what is the continuous spectrum, guys? Again, this is something which you have learned previously. So the spectrum which constitutes of all the wavelengths is called the continuous spectrum. For example, this diagram, if you see over here, there is a continuous spectrum. As you move from left to right, you can see that there are gamma rays and there are long radio waves over here, right? So each and every frequency and each and every wavelength is being accounted for, and that is present in this spectrum. And if you magnify this small part, which is the visible spectrum, you can see this as the visible colors. The other part, they are not visible to the human eye, right guys? So it consists of all the wavelengths. But what happens in a light spectrum, guys? In light spectrum, which is also known as atomic spectrum, there is no such thing as continuous wavelengths. This continuous word is wrong in this case. So a spectrum in which only specific wavelengths are present is known as a line spectrum. For example, this diagram. So if you see that diagram, you can see that it has bright lines with dark spaces with them. And the bright lines, these are the spectra which I'm talking about. Whenever there is a dark space, there is an absence of the wavelength over there. So it is not a continuous spectrum as you saw in this case, right guys? So in this case, there were continuous spectrum, each and every wavelength existed. While in this case, if you see this diagram, there were some black spots in between, and these black spots denote there is an absence of a wavelength over there. That is why it is known by the name line spectrum. You can see these lines over here, guys, right? So this is why the name line spectrum came, and this is shown by atomic particles such as electrons. Hence atomic spectrum is also given to this phenomena, right guys? So we studied about spectrum and its two types, which is the continuous and the line spectrum. Let's further our discussion now, guys. So talking about atoms now and subatomic particles inside atoms, the electrons which are there, it can absorb as well as emit some radiation, right guys? So this section is about those electrons, those subatomic particles, guys. Okay, so whenever electromagnetic radiation interacts with matter, by matter I mean atoms, molecules as well as the subatomic molecules, right? Subatomic particles as well. So what happens is when electromagnetic radiation interacts with these sort of matter, what happen is they can absorb the energy and reach to a higher energy state. Okay, so these atoms over here, they are absorbing energy, and initially they are in a stable state, guys. And whenever there is an absorption of energy by these atoms, they will reach at a higher energy state. This is known as the excited state, and this will be an unstable state for them. So with higher energy, these are in an unstable state, guys. It is not possible for the atom to stay in an unstable state for a long amount of time. For a split amount of time only it will be there, right guys? So instantaneously what will happen is, for returning to the normal, which is the more stable and lower energy state, the atoms or the molecules, they will emit the radiations now, okay, in various regions of the electromagnetic radiation. So to return from that excited state to back to the normal state, which is the most stable state, it will emit the radiation, it will emit the energy which it had initially absorbed to reach the excited state. So that is why you can see an absorption of energy happening over here and emission of energy which is happening over here, hence the name emission and absorption spectra. Now whenever there is an emission or absorption, you will perform an experiment and there will be formation of a spectrum, right guys? So what is the emission spectrum, guys? The spectrum of radiation which is emitted by a substance. So whenever a substance is at the excited state and it comes back to the normal stable state, it will emit the energy, it will emit the radiation. This is known as the emission radiation, guys. And it has absorbed energy, right guys? So the initial state had some absorbed energy, that is, it's in an excited state, and this thing is known as emission spectrum. So similarly, we can define what is absorption spectrum then. So absorption spectrum is the spectrum absorbed when radiation is passed through a sample of material, right guys? Whenever you have a sample which is in the very stable state and you pass on some radiation with them, right? So you're giving some energy, you're imparting some energy to the stable state, and you will see that the atoms, the molecules, they will absorb the energy which you had given and they'll reach at the higher excited state. So the radiation which is absorbed, the spectrum which is formed in that case, is known by the name absorption spectrum. And the sample absorbs radiation of only certain wavelengths. It is not a continuous wavelength, guys. It will be only a certain wavelength, right? So let's move on. So we come on to the second topic. Now this is an interesting section of this video. So Rydberg equation. So Mr. Rydberg over here, he performed some experiments and he gave us an equation which we'll study over here. So before we move on to the Rydberg equation, let us summarize what all we studied. So electrons, as we said in the previous section, it may absorb energy when going from stable to an excited state. Whenever you impart energy, it goes from stable to excited state and the electrons will absorb the energy in that case. And whenever it has absorbed the energy, it will reach at the unstable state, and because that is an unstable state, the electron would want to come back to its stable state, and hence there will be emission of energy. Hence the electrons will emit energy now when going from excited state to a stable state. So if you see this electron, it is at a very stable position, and when you give energy to this electron, it will move out to maybe n equals to 3. N is the orbit number over here. So initially n was equal to 1 for this electron, and this electron, because it has absorbed some energy, it will go to third shell, n equals to 3. So at n equals to 3, it is at a unstable position, guys. So therefore it will come back to the n equals to 3 to n equals to 1 now. So this is how both absorption as well as emission of radiation will occur. So electrons have lower energy at the lower orbit numbers. So it has the lowest energy in the n equals to 1 and it has the highest energy in n equals to 3 over here. So when will the energy be absorbed, guys? Electrons move from lower to upper orbit. So whenever electrons move in this direction, it means the electron has absorbed some energy, and hence it was possible for the electron to go from a lower orbit, which is a lower energy state, to a high orbit and a high energy state, guys. So there was absorption of energy in this case. Similarly, the electrons will emit energy when they move from upper to lower orbits. So whenever it's present in this state, it is an unstable state, higher energy, it will want to move to the nearer to nucleus, which is at the n equals to 1 state, right? So it has the lowest energy in that case. So Mr. Rydberg over here, he gave us this equation and he said this radiation, what is this radiation? Whenever there is an absorption or whenever there is an emission of radiation, so this radiation, it has some wavelength, guys. Okay, so every radiation will have a wavelength, and this is the equation which will give us the wavelength of the emitted or the absorbed radiation, guys. So 1 by lambda, this is also known by the word wave number. So if you have lambda, what is wave number? It is nothing but 1 by lambda. The reciprocal of the wavelength is known by the name wave number. It has the units meter raised to minus 1. Okay, so the wave number is given by this equation, which is RH, and inside brackets we have 1 upon n1 square minus 1 upon n2 square. Now what is RH, guys? RH is a universal constant. Irrespective of the atom which you use for the experiment, it is an universal constant known by the name Rydberg's constant, and it has this much value. Okay, and n1 and n2 are the orbits over here. You saw there are 3 orbits. So here n1 is less than n2 for us to arrive at a positive figure, right? If n1 is less, this figure will be more, and the more figure minus the lesser amount of figure will give us the positive number as a whole. So that is why we take n1 minus n2, and these are the orbit numbers, as I said, guys. Okay, now there are some names which are given to the specific line spectra. So depending on the value of n over here, the various names have been given. There is no logic behind these names. You just have to remember the names in this case. So scientists have performed various experiments in hydrogen atom, and they have arrived at various series. So whenever you have the lower orbit as 1 and the upper orbit can be anything more than 2, then the name will be Lyman. Similarly, when n1 equals to 2, n1 is the lower orbit out of these two, right? And n2 is the higher orbit, as we said. So n2 is 2, we have the Balmer series. Next, we have the Bastian, we have Brackett, and we have Fund. So Lyman, Balmer, Bastian, Brackett, and Fund. You need to remember these names, and based on n equals to 1, we have Lyman. Similarly, n equals to 2, we have these names over here, which is represented using this diagram. Now this is n equals to 1 over here, guys. The nucleus is lying somewhere over here. So n equals to 1, n equals to 2, and 3, and so on up till infinity. So anything which is reaching n equals to 1 over here. So if you see these rays over here, there is n equals to 1, and all the other end points are lying somewhere at greater than n equals to 1, which is this first case, and hence all these will be named by the name Lyman series, which is an ultraviolet series, right, guys? UV series. Similarly, we have the Balmer series now. So Balmer series, the lowest n1 is 2. So at n1, which is 2, we have all these lines, all these spectral lines, and this is the visible range, guys. Okay. Similarly, we also have the Bastian, which will end at n equals to 3, right, guys? So n equals to 3 is coming from over here. So this is the Bastian series. So this is a pictorial representation of this thing over here. You just need to remember these names. So with this, we reach at the end of the video, guys. Let's summarize quickly what all we learned. We studied about the two types of spectrum, which is the continuous and the line spectrum. Line spectrum is the discrete spectrum, also known by the name atomic spectrum, guys. Then we said that the electrons in an atom, they can emit or they can absorb the radiation. And whenever there is emission, we have the emission spectrum, and whenever we have absorption, we have the absorption spectrum, guys. Okay, then finally we came on to the second section of the video, where we learned about the Rydberg's constant and the Rydberg's equation, which is this equation, right? So whenever there is an absorption or emission of radiation within an atom, you can find out the wavelength or the wave number of the emitted or the absorbed radiation using this equation, right? Here RH is the universal constant, Rydberg's constant, and n1 and n2 are the orbit numbers, right? So various line spectra have the different names. We also studied about the different names. If n1 is equals to 1, we have Lyman. N2 equals to 2, we have Balmer. N1 equals to 1, we have Lyman. N1 equals to 2, we have Balmer. And similarly and so on. We have Bastian, Brackett, and Fund as well. So this was the summary, guys. Thank you for listening to me in this video. And in the next section, again, we'll talk about something about atomic spectra, and we'll move on to the Niels Bohr's model as well. So how Niels Bohr used all these concepts together, all the three parts which we studied in this video, and he used all these concepts to develop his own model, which is known today by the name Niels Bohr's model. And as always, if you enjoy watching my videos, you can follow me over here, and you can ask me any doubts if you have in the comment section. Thank you, guys. Take care, and bye-bye.